Okay, good afternoon everyone. Well, in South Africa it's afternoon already, so I suppose depending on where you are, it may be good morning. Welcome to another session of the Flownex webinar series. Today we will be looking at valve sizing for controllability, as you might know. My name is Rolf Lawrence. I'm a senior engineer at Flownex, and I've been working with Flownex for the past, let's say, about 10 years. And in that, I must admit, I really saw some great advantages of the software we're using, that especially in systems where I need to use control valves, need to size valves, even size pumps, and they go hand in hand together. So today's session, I'm quite excited to share with you some of the knowledge. I'm by no means an expert on this field, but I have used it before, and I would just like to introduce to you the capability of Flownex to help the engineer in selecting the right control valve. From the attendees, I see there's a few new guys, names that I don't know. So I'll start off with a quick introduction of what Flownex is and where it can be used, just to get everyone on the same page. So let's start right off. Just by the way, you'll see on the right-hand side of your screen, just alongside the GoToWebinar tab, that there is an icon with a yellow hand on it. So if you press that icon, you'll be able to type a question to me, and I would invite you to please do that, or otherwise you can just unmute yourself and interrupt me to ask a question verbally. So either of the two ways, you're welcome to ask questions at any time, either by, we call that raising your hand, or then as it is, press that yellow hand button, or then also to interrupt me by unmuting yourself. Okay. So Flownex was founded in 1987. So you can see that we've been on the map for quite a long time. And in that time, we've developed to become quite a substantial software, if I might call that myself. The second bullet there, Flownex is developed in an ISO 9001 and an NQA1 quality assurance system environment. That sounds pretty impressive, and in fact, it is. Flownex is the only software of its kind to hold a nuclear accreditation. And that's a testament to the quality, reliability, and accuracy of our simulation software. Just as a side note, we've been developed, or Flownex has been developed between, what was it, 1996, I think, roundabout, up until 2008, with close collaboration with the PBMR, that's the Pebble Bed Modular Reactor. And in that time, that's where the nuclear quality accreditation came from, because we had to adapt to their kind of systems and quality. And also that shows that we are focused on the power industry, and then also on the turbine industries, and we'll go through the industries in just a second. Okay. We'd like to summarize ourselves as a system simulation software for process flow and heat transfer. Okay, so that's a short sentence. I'm quickly going to elaborate a little bit more on that. Flownex is an engineering software that accurately models flow of fluids and heat transfer in industrial plants. It is tailored for the design and analysis of power plants, and that includes all the auxiliary systems. Also aerospace, HVAC systems, and then water, slurry, oil, and gas handling facilities. The plant components are linked together when we build the models using the drag and drop convention from extensive component libraries, which are based on fundamental principles and empirical data. The term simulation environment comes from the fact that it is a platform to initiate personalized command coding and then also third-party software simulation. And that enables you to generate a vast variety of solutions in state-of-the-art industries. As you can see on the screen, there's just an example of a script that you can type in order to add your own, say for instance, heat transfer coefficient, if that is not available in Flownex by itself. So it really gives you the full freedom to add to what is already there if need be. These are some examples of a third-party software that you can automatically link to with Flownex. You can see the Fluent, ANSYS, MathCAD, LabVIEW, Excel. All of these can be used together with Flownex simultaneously. We call that co-simulation. Flownex calculates flow rate, pressure loss behavior, heat transfer rate, and all significant fluid properties in both transient and steady state. And that significant fluid properties that we are talking about is stuff like densities, viscosities, Reynolds numbers. So all the information that's required to the engineer in terms of fluid mechanics and heat transfer, that is where Flownex focuses on. It reliably simulates flow branching, flow and thermal inertia, water hammer, choked flow, buoyancy-driven flows, and combustion and swirl effects. And all of these makes it perfect for simulation of, let's say, for example, power plants where you have startup and shutdown scenarios, and you need to include the inertia of the turbo machinery or the pumps, and then also of the fluids itself. It allows the use of liquids, gas, two-phase flows, slurries, and then, or any combination of these fluids. So I can mix water with air, and then Flownex will enable me to calculate the correct fluid properties. It establishes a fundamental understanding of individual component and complete plant or system behavior. And that's also where I personally found a lot of benefits in using this over the years. There's an example of a smallish network. This is just a refrigeration network, and then you can also use Flownex to increase the type of detail or the kind of detail. And this is an example of a process flow diagram level of a coal-fired power station. So this will be the Flownex interface, or the Flownex component interface, and you can also create a human-machine interface, as we call it, or a SCADA, depending on the function, where you have images that helps you to visualize the results. There's an example of how to interact with the network. So these valves, you can click on those valves and they will change color, and also then in the background open or close the valve itself. In Flownex, you can start up and shut down the pumps. So you can control the network from an interface like this, and not necessarily just on the Flownex network itself. We also have fluid properties. This is an example of a TS diagram, but more or less any kind of fluid property diagram that you would be interested in. And again, this helps you to visualize or understand what goes on in your network. And this is just an example of a dynamic simulation or a transient simulation that we ran. What happened here is we closed this valve. The valve closes quite suddenly, and then the pressure waves through the network can then be plotted on this graph. So with this in mind, you can imagine that you can use Flownex to, it's a dangerous word, but to say to basically solve any kind of thermohydraulic problem. And yes, obviously each type of software has its own specialities and its position or its place where it fits in. And although Flownex is not the best tool for everything, I mean, you have CFD like ANSYS, which perfectly fits into the place. You have other kinds of software that has its place. But Flownex enables you to do so much, and therefore, it's just such a pleasure to share this with you guys. Our international footprint, there you can see by the blue coloring, that's where we are currently presented all over the world, and obviously we're working hard to get that image even more painted with the blue. That was the background. Obviously, you guys are all tuned in for the valve sizing for process controllability, and I'll start right off without further ado to go on with that. So let's go to Flownex. Okay. Here I've set up a Flownex network, and these are 3 pipelines. They use water as the liquid. And as I showed you earlier, these components have been dragged and dropped from our component library in order to form these networks. The first example is a pipeline of 10 meters on both sides of the valve. The second one will have 100 meters on both sides, and then the third one will have 1,000 meters on both sides of the network. Then we have the valve, which is identically the same valve for each case, there, and there. And the reason why I start off with this is to bring home the importance or the impact of the system on the valve. If I want to size a valve for a typical system, I cannot look at the valve by itself as it is only there. I need to incorporate the whole system. And I will show you in just a minute why that is important by the results that I got here. So I'd say that's the first advantage that Flownex gives you when doing valve sizing like this. These are fairly simple network layouts. But you can imagine for, let's say, a power plant where you have a lot of the different components that all impact on the system and all has various kinds of flow resistances. And that has to be incorporated in the selection of the valve itself when we are doing that. The second thing, as with any software, but especially with Flownex, in this case, is the inclusion of all the correlations that is needed to calculate that. Now for control valve, I quickly go to the Flownex library or the Flownex help manual. Just scroll up a little bit. You can see there's all the information of the functioning and the theory behind the valve. What I want to get to is this equation. So this is just for when I have a liquid as fluid in my pipeline. This is the equation that will be used in order to calculate my mass flow. And these constant N1, Fp, or these factors, and Fr are all calculated based on the Reynolds numbers and then also the geometry of the piping and the valve itself. And that can be quite tedious, but as I said, that's luckily with Flownex, and as I said, with any other software that's specifically built for valve sizing, that will already be built in. So this helps a great deal in order to get to the solution as fast as possible. To quickly run through the inputs of the valve itself, by default, the valve assumes the same diameter as the neighboring pipe, but you can also change that to say the pipe different or pipe diameter is different from valve diameter. Let's state that as yes, and then you'll see the other inputs opening up. And there I can specify the valve diameter and then the pipe diameters on both sides, and that will help Flownex to calculate the loss factors as it goes, or also the CVs into the CV relations as it goes from the pipe into the valve. For now, I'm going to leave that at no, as it was by default, just to make things simple. I can also select where the valve needs to get its diameter from, and then the valve flow characteristics. Here I have the valve flow behavior, and it can be either a linear behavior or equal percentage, in which I need to specify the rangeability as well, or then I can select a chart from the Flownex library, or I can create my own chart if need be of that valve. For now, let's start off just with a linear valve or a linear response valve. Then the CV value, I can give that input, and then I can select if I need to ignore the choked flow conditions, which normally wouldn't be a good idea. And then for liquids, I have the FL factor. Now that one, that is the liquid pressure recovery factor. And that is to account for the influence of the internal geometry at vaporized or phase change flow. So normally like blowdowns, or when I have really, really high velocities high velocities in my pipeline, then that is important to have that value correct. When I go to gases, like this air example, then that value will automatically update in order to require the XT factor, and that is the pressure drop at which the compressible flow, or the pressure drop ratio, sorry, at which the compressible flow will start to choke in the vena contractor. These values are extremely important in selecting the type of valve. And just to quickly take you through that, you can see in the Flownex manual, if I scroll down a little bit, just to this chart, depending on the type of valve, these values will differ quite significantly. So as I scroll through this, you'll see that, say for instance, for a globe valve, then a rotary valve, the FL and XT values will differ quite significantly. So it is extremely important when you have a type of valve in mind in order to have the correct values, or then later on to design for a value in which you can then from that value then go and select the required type of valve. Okay, so just keep that in mind. These values are extremely important when you need to size a valve or select a valve. To go back to the system performance as an example, I want to take you to the results. So what I've done is I've set this up at various openings of the valve, and then I wanted to see what would be the flow through the system or through the pipeline and compare that to the different pipelines. So there's my in total 20-meter pipeline, that's in total 200 meters, and this is in total 2,000 meters. If I go to my Excel sheet, there I can see, so this is my 20 meters volume flow versus valve opening, my 20 meters pipeline, my 200 meters pipeline, and then also my 2 kilometers of pipeline. And you can see here that the selection I had was linear. So when there's little contribution by the system in terms of losses, I will pretty much get my linear response. But the greater the system resistance when compared to the valve resistance, the more I would deviate from that linear response. And that might force me to go to a valve that is rather equal percentage. So the curve would look something like that for the valve itself, and that will then bring down this line if I want to have a linear response by my system. Okay, I hope you guys understand that. I'll explain that a little bit more as we go on. Just for interest sake, here's the one for air. So there you can see again, there's the short pipeline in blue, and as the pipeline resistance increases with relation to the valve resistance, that curve deviates quite a lot. So it is from this, I hope you can see that you cannot look at the valve itself only when sizing the valve. You need to incorporate the complete system. I have a small list here which I set up for myself on how to do valve sizing, and I want to quickly run through that with you guys. So the first one will be obviously to define the system. And that is just to see which do you have a pump or not, what is the type of pipe lengths, other components like heat trans, like heat exchangers and all of that, what is in your system, so to define your system. Then step 2 is we need to define the pressure drop for the fully open valve. That is usually, as a rule of thumb, you can use a value of about 10 to 15% of the total pressure drop of the system at maximum flow, obviously, and then or 50 kPa of pressure drop, whichever is greater. So that's just a rule of thumb. Step 3 will then go over, having decided on this pressure drop that we need over the valve when it's fully open, we can calculate the CV of the valve, so that's the loss coefficient when the valve is fully open. And then later, the next step would be to do the preliminary selection of the valve, and then that would also include to the step to select the minimum and nominal flow of the valve stroke. So we would say, for example, when the valve is 20% open, then we would, let's go back to the linear response, then we would need 20% of the flow, and if the valve is 50% open, we will then need 50% flow. There may be some other conditions or other plant setups where you would not ideally choose the linear response, but rather some kind of other system response. But you have to have that in mind beforehand. So that will be the minimum and nominal flow and values against the valve stroke, or then you can also say the system performance shape. It's good to keep in mind never to use a valve that is less than half the pipe size, And then also to avoid the lower 10%, or you can rather increase that to 20% maybe sometimes, and the higher than 80% of the valve stroke. So try to stay within 20 and 80% of the valve opening. And then lastly, check your gain across the applicable flow rates to ensure that you have a gain of more than 0.5. And the gain is just an increase in percentage of flow in ratio with the increase in the delta stroke, or the percentage delta stroke. Okay, so let's follow these steps and then see if we can get to a valve. Okay, so we already defined the system. Let's go back to Flownex. Let me go to page 3. So there's a gravitational flow. I'm going to delete this valve to do it from the start. So there's my system. I have a reservoir that is up on a hill, and then I have a 200-meter pipeline, and then that goes out into atmosphere. Okay, so that's my system. Next up, I need to define the pressure drop according to step 2. So define the pressure drop for a fully open valve. Now I can select a percentage pressure drop of 10 to 15%. For now, I'm going to keep it simple and just assume a value of 50 kPa. So I can drag and drop my ANSI control valve. And then what we need to do is I'm going to assume the same diameter as that of the pipe. I'm going to select to start off with the linear valve behavior in order to test if that's happening. I'm going to keep the default values for FL just for now. And then for this one, I need to calculate the CV value. Okay, so that is then step 3, calculate this valve at fully open condition. So I'll go to my valve, set the valve lift or fraction opening at fully open, and then let's start off with a value of 50 and see where we get to. So I can solve it, and then I can go to the results page of the valve, and here I'll see a pressure drop of 108 kPa. And just to make things easier, I can drag and drop this result, click, drag and drop it onto my canvas, and then I can see that the whole time. Let's take mass flow as well as a result. So from this I can see that if I want to get to 50 kPa, I need to do something to reduce that pressure drop, and that would then be to increase my CV if I then look at the definition of CV. Now I can do that manually, or Flownex enables me to do this quite easily by using the designer. Now that's something similar to the goal seek function in Excel. Let's quickly set that one up. So I can go to configuration, designer setup. Let's create a new one. You can see I've done quite a bit of them. Add, let's see, valve gravitational CV. So I want to achieve a target value of 50 on my pressure drop. That would be my goal. And then I need to achieve that by changing the CV value. Now I know 50 is not enough, so I need to start off at 50 and a maximum value of 150. Then I can go to my home functionalities and say run designer. Okay, so there you can see I found the value of exactly 50 kPa, and that's where we want to be with the valve fully open. Okay, so you can see the CV here is at 100. Yes, I must admit I've designed the system previously to end up at a CV of 100. So it's not coincidence. This is by, you can call it back engineering, that I've done this prior to this webinar. Okay, so we now know that the CV value at fully open should be 100 in order to get a 50 kPa pressure drop. Next up is the selection of the minimum nominal flow or valve stroke, or then the system performance shape. Okay, so I'll just say that I want a linear system performance, or as close to linear as possible. And let's see what this valve does just as it is here. In order to get that, I can run a sensitivity analysis. So let's quickly do that, set that up. What I can do is, in this sensitivity analysis, I can then tell Flownex to solve the network at various openings, and then from there get the information from Flownex, and I can put that into Excel and then draw some graphs. Now, I'm not going to do that now because that will take up an unnecessary amount of time. But where we will end up with this, if I go to my Excel, that's what I've created here. The blue line in this case will be the setup as it is there. So this is my linear response. And you can see that's the influence or the deviation from my linear control line that is due to resistance of my network. So that's the blue line here. And if I were to change this to equal percentage, then the with a rangeability of 50, and I do that same sensitivity analysis again, I would end up at the values as visualized by this blue line. So from this I can see that probably if I use the linear valve, I would be the closest to get a linear response. And I can now go a step further. I can go and design a valve chart that would give me a flat response, or not a flat response, a linear response. Okay, but we're just going to stop here for now. So you can see that if I were to select between the two, then I'd rather go with a linear valve. Okay, just to take a step back out of what we are busy doing in Flownex. If I talk about a linear valve or equal percentage valve, just to take you quickly to what that is. So you will see by the percentage of flow and by the percentage of valve lift, if it's only the valve itself, an equal percentage valve will give me this response. So in the beginning, with a lot of movement, I'll only get a small amount of flow increase. And then for this one, the quick opening valve, with just a small amount of movement, I'll get a lot of flow percentage increase. So these are the three main types of valves: quick opening, linear, and then equal percentage. So that is what I'm referring to when I look at that. So that will be for the gravitational system. I've done the same with a pump feed system. So here I have a pump included, and the difference between the two will be the gravitational feed system's inlet pressure will stay constant because there's nothing changing it. And with the pump, as I change the resistance by the valve, that will also influence the pump chart, as I can see it here. And then that will again influence, obviously, the valve curve, or the pressure drop over the valve, and then also the flow through the system. So I've done that, and that gave me the results as showed here by the red line. So this will be for a linear valve, and that will be for an equal percentage valve. And just looking at these graphs, you will see that if I'm looking for a linear response by my system, when I'm looking at the gravitational system, and that is for this one, for the 200 meters lines. If I have a different system, it will have different results. But for this system that I was modeling, I'd rather go for the linear valve when I'm having the gravitational system. When I look at the pumping system, in my example, then I'd rather go for the equal percentage valve. Okay, and again, I can now go and I can tweak these values. I can design my own valve chart. With that being done, I can now go to the manufacturer, to the valve manufacturers. I can tell them, okay, I need a valve that responds in this certain way, and then I can tell them a linear valve with a certain CV, or equal percentage valve with a certain CV and rangeability, or then I can give them the graph that I designed for my system. They will then give me a valve that responds close to that, and what they will give me looks something like this. This one. So here I can see a spec data sheet of a random selected valve with a minimum value, a normal value, and a maximum value. With this, I can go back to Flownex, I can go back to my model, and I can go to charts and lookup tables, and then create a new chart. Something like this. Oh, that's the pump chart, sorry. I need to go to valves, and I can create a new valve. Something like this, which has these values depending, or that has been determined by the manufacturer, and now I can model the exact values or the exact response that I should be getting from this valve. That will then tell me if I did the right design or the wrong design, and I can repeat the process, or I can say this is exactly what I want. Okay, I hope you guys are still following. The last thing that I want to show you is how this will look when I finished my design. And as an example, quickly just want to take you through this. This would be a generator cooling network. So here I will have a generator with total of 100 kilowatts input into it, depending on the plant load. This will be hydrogen, which cools down my my generator, and that will be cooled down by a water network. And this is my control valve that I need to size, or that I needed to size, and that I'm going to control now for you guys. So let's go to this Flownex network. So here you can see the Flownex network. This is my hydrogen system here. That will be my heat exchanger, and that will be my water system. Okay, here's my valve. That's my controller, my PID controller in Flownex. And you can do a steady state solve, and then I can run the simulation. And I can see the results on this HMI that I created. That will display the pump chart, and here I'll see the temperatures and then also the valve opening as it changes up. This is the plant load, so I've predeterminedly set up a certain plant load response, and I'll just show you guys that while the simulation is running. So I'm going to start that. The purpose of the simulation is to get this temperature to 44 degrees C. So you can see at the beginning of the simulation, it is a little bit too hot, so it needs to cool down at a plant load of 80%, and my valve is opening in order to allow more water through that. As soon as I get to 20 seconds, the plant load will suddenly increase to 100, and with that, a sudden increase in temperature in my hydrogen system. That will cause my valve to open, as it does there. And then when I get to 30 to 40 seconds, the plant load will start to decrease steadily. That will then cause a decrease in temperature, and the valve will need to correct that in order to get my temperature back to 44 degrees C. Okay, so this is an example of how things can look like in the end. As you can see there, this valve is controlling very nicely between a 30% and 70% opening, and the response is quick enough not to let the network run away. And obviously, this is where we would like to end off with any system. Okay, that is what I had in mind to show to you guys today. Again, this is not to teach you in detail how to use the tool, but rather just to show you, or to exhibit, what the power of Flownex is when I need to size a valve, and how I can apply Flownex in order to get to the result quickly. If there are any questions, you guys are welcome now to ask a question, or then also to just press the hand icon and then type a question. I'm quickly going to unmute all of you, so you are welcome to then ask a question. Okay, it seems like I don't see any questions. Okay, so that either means that I've done quite a good job in explaining this, or that I've done the worst job ever and none of you guys have a clue of what I just said. I hope it's the first one. Anyway, you're welcome to send me an email afterwards. You can go to our website, www.flownex.co.za.com, and then send us an email, and we'll respond to that as soon as possible. So you're welcome to contact us. Please send through the questions, and we'll attend to you each individually if need be. Otherwise, just for any other questions, also feel free, and you're welcome to contact us, and we would gladly like to help you. that's all for today. Thank you for joining in. I appreciate your time. We've gone over the time just for a little bit, but I hope this has been helpful in showing you guys how Flownex can be used in order to size a valve. May you have a wonderful day, and then also I believe I won't be speaking to any of you before New Year's time, so when the New Year's come, I hope that you have a wonderful new 2017, and for those of you who are going into the festive season, may that be blessed, and may you have a wonderful time with your family. Bye-bye.